Is that an isocline? Well, wait a minute. That doesn't correspond to anything looking like this. Aha, but it would if I put C multiplied through by C. And then it would correspond to C being 0. In other words, don't write it like this. Multiply through by C, it will read cy equals negative x. And then when C is 0, I'll have x equals 0, which is exactly the y-axis. So that really is included. How about the x-axis? Well, the x-axis is not included. However, most people include it anyway. This is very common to be a sort of sloppy and bending the edges of corners a little bit, you know, and hoping nobody will notice. We'll say that corresponds to C equals infinity. I hope nobody wants to fight about that. If you do, go fight with somebody else. So if C is infinity, that means the line, little line segment should have infinite slope, and by common consent, that means it should be vertical. And so we can even count this as sort of an isocline, and if, you know, I'll make the dashes smaller to indicate it has a lower status than the others. And I'll put this in, do this weaselly thing of putting it in quotation marks to indicate that I'm not responsible for it. Okay, now, we now have to put in the integral curves. Well, nothing could be easier. I'm looking for curves which are everywhere perpendicular to these rays. Well, you know from geometry that those are circles. So the integral curves are circles. And it's an elementary exercise, and of which I would not deprive you of the pleasure. Solve the ODE by separation of variables. In other words, we've gotten so the circles are ones with a center at the origin, of course, equals some constant. I'll call it C1 so it's not confused with this C. They look like that, and now you should solve this by separating variables and just confirm that the solutions are in fact those circles. One interesting thing, and confirm this, I won't do it because I want to do geometric and numerical things today. So if you solve it by separating variables, one interesting thing to note is that if I write the solution as y equals y1 of x, well, it'll look like something like the square root of C1 minus, let's make this squared because that's the way people usually put the radius, minus x squared. And so a solution, a typical solution looks like this. Well, what's the solution over here? Well, that one solution only goes from here to here. If you like, it has a negative side to it. So I'll make, let's say, plus. There's another solution which has a negative value. But let's use the one with a positive value of the square root. My point is this, that solution, the domain of that solution, really only goes from here to here. It's not the whole x-axis. It's just a limited piece of the x-axis where that solution is defined. There's no way of extending it further. And there's no way of predicting by looking at the differential equation that a typical solution was going to have a limited domain like that. In other words, you can find a solution, but how far out is it going to go? Sometimes it's impossible to tell except by either finding it explicitly or by asking a computer to draw a picture of it and seeing if that gives you some insight. It's one of the many difficulties in handling differential equations. You don't know what the domain of a solution is going to be until you've actually calculated it. Now, a slightly more complicated example is going to be, let's see, y prime equals 1 plus x minus y. It's not a lot more complicated. And as a computer exercise, you'll work with still more complicated ones. But here, the isoclines would be what? Well, I set that equal to C. Can you do the algebra in your head? An isocline we'll have the equation, this equals c, so I'm going to put the y on the right-hand side and that c on the left-hand side. So it will have the equation y equals 1 plus x minus c. Or a nicer way to write it would be x plus 1 minus c. I guess it really doesn't matter. So there's the equation of the isocline. Let's quickly draw the direction field and see what... notice, by the way, it's a simple equation, but you cannot separate variables. So I will not, today at any rate, be able to check the answer. I will not be able to get an analytic answer. All we'll be able to do now is get a geometric answer. But notice how quickly, relatively quickly, one can get it. Some feeling for how the solutions behave to this equation. All right. Let's see. What should we plot first? I like c equals 1. No, don't do c equals 1. Let's do c equals 0 first. C equals 0. That's the line y equals x plus 1. Okay, let me run and get that chalk. So all isoclines are in orange. If so, when c equals 0, y equals x plus 1, so let's say it's this curve. C equals 0. How about c equals negative 1? Then it's y equals x plus 2. It's this curve. Now let's label it. Let's label it down here. So this is c equals negative 1. C equals negative 2 would be y equals x. No, what am I doing? C equals negative 1 is y equals x plus 2. That's right. Well, how about the other side? If c equals plus 1, well, then it's going to go through the origin. Looks like a little more room down here. How about that one must, so if this is going to be c equals 1, then I sort of get the idea. C equals 2 will look like this. They're all going to be parallel lines because all that's changing is the y-intercept as I do this thing. So here it's c equals 2. C equals, that's probably enough. All right, let's put in the line elements. All right, c equals negative 1. These will be perpendicular. C equals 0, like this. C equals 1. Oh, this is interesting. I can't even draw in the line elements because they seem to coincide with the curve itself, with the line itself. They lie along the line, and that makes it hard to draw them in.